Yo, what's up, everybody? Welcome back. Today we are working on my virtual GPU, and today's topic is triangle interpolation. We are working on a virtual graphics card. The idea here is that we put a fake GPU into QEMU, a virtual machine. We write a kernel driver for it. We write an OpenGL driver for it, and as we get to something that is functional, we will get some form of idea of what a GPU would actually do in the real world, with the intent of someday grabbing an FPGA and trying to make one ourselves, right? We are at the point right now where if I run this application, we can see that here in QEMU I have a little Sphero GPU, and here we are running an OpenGL application that draws a simple triangle and clears the background with varying colors. That's pretty cool, right? And this actually is a significant amount of work, right? Because drawing a triangle is not as simple as saying, GPU, draw a triangle. In the OpenGL world, specifically in like Mesa's implementation of the OpenGL world, where Mesa is a library that implements OpenGL for a bunch of GPUs, including our new GPU, he requires the use of shaders. So a shader is basically an arbitrary program that you run on the GPU. And in the typical OpenGL graphics pipeline, your shaders you need at the very least a vertex shader and a fragment shader. So the idea is if I'm looking at this cube in the world, right, the cube has a bunch of vertices, right? And if I am like zooming in and zooming out, even though like in the world, if in like the world, the cube is not moving, he's kind of in the same place. We're just kind of moving our camera around. From our perspective, it is moving, right? And so you need some way to control, like, well, if I want this thing to be bigger or smaller, I need to be able to like move those vertices around. If I want to move everything along the y-axis, right, then I need to be able to like programmatically say that. And so what you do is you write these programs where like we have a vertex shader. Our simple vertex shader basically says, hey, don't move this thing. Don't do anything. But if you wanted to like move this thing to the left, you could do like a pause dot x plus 5 or something would move the thing 5 units to the right, right? And so as a developer of a 3D application, you basically write these programs that have inputs and parameters that you can like adjust over time with some data, and it will like mathematically transform these vertices. So in order to draw our simple little triangle demo, we actually need to implement a program that does nothing to the triangle that are input, essentially. Then you have this thing called a fragment shader, which says, okay, so we found like the 3 corners of our triangle. Now, what color do we make each pixel in this thing, right? Because the triangle is made up of many, many pixels. In our case, right now in our simple application, we have just output 1 color. Great. Now, if we wanted to do anything advanced, like sample from an image, right? You want to like take a triangle and you want to put a picture on it. You would need to like for each pixel, figure out where to look at the picture to put the thing, like where in the picture that pixel should come from, I guess, right? Or if we want to do something simple, like this diagram I drew just before stream, say we wanted to like make a triangle that had some gradient from red, green to blue. What you would do is you would attach red to one of the vertices, green to another vertices, and blue to another. And what we would have to do is then interpolate these values in the triangle so that like as we move along from like this blue dot red dot to this red dot, we would have to basically get more and more red as we walk this line, or more and more green as we walk this line, or vice versa, which gives us this like kind of like gradient of red to green to blue in here. So there are 2 things that we need to tackle today. One is that we need to support providing an input to this fragment shader, right? So in order for this fragment shader to change its behavior based off of where it is in the triangle, we basically need to input like a color here, right? Then from the vertex shader, what we would do is we would attach red, green, and blue to each of these vertices, pass it along, and then when our graphics pipeline tries to render this thing, he needs to call the fragment shader for every single pixel in this triangle with the interpolated value. So the plan of action is to basically like implement this for our little demo application. We will then immediately start crashing, right? Because our implementation of our shader compiler is only implemented for whatever commands happened to exist in the existing shader. As soon as we start adding more, those things will not be true anymore. We're gonna have to fix that. Once we have a compiled shader, then we're gonna have to actually do like we're gonna have to like implement barycentric coordinate mapping or something to do some form of like how do we know at each pixel in this triangle how much of it is red, how much of it is blue, half of it is green, and then if we get through all that, hopefully we see something pretty. And that's the plan of action, and I think we just jump in. So I think we start here by adjusting our vertex and fragment shaders to basically say we are going to output a color for this thing. And maybe we have something that's like vec3 in color. And maybe we will just pass that color along. I think that's how you do this. I haven't worked with like old GLSL that much, so I'm not really 100% sure that this is right. But we'll kind of just start here and see what happens. Then in our fragment shader, we're just going to use this color. Like this. And hopefully if we did everything out right, this will work. So can we try to run this on an existing GPU? Right, so we have like the GPU that we're implementing, as well as the one that like most anybody who uses QEMU for real would use. And so let's start there. So we need to click a button here for it to work correctly. I think we need to like go here to initialize the vert.io GPU, and then we can call this. And okay, so this is not good. We're seeing totally black. But so it looks like our shaders are working, but we have forgotten to specify the attributes to the shader for our different colors. So we'll go into our test app. Where the fuck are we? Main, I guess. And we just need to make sure that our vertex data now has RGB. So we're going to go red. And then we're going to go green for the second vertex and blue for the third. And this is kind of like each of these lines represents like one item that's an input to the vertex shader, right? So the first three things are going to be its X, Y, Z coordinates. So this is going to be the bottom left, bottom right, and top pixels. And so the bottom left should be red, bottom right should be green, top should be blue. Now we have to tell the OpenGL system about how these things are going to be, how this data is structured, right? So I think, let's look up the definition here of GL vertex attrib pointer. I can never remember exactly what these things are. Oopsies, let's keep this here and go like GL vertex attrib pointer. So we have the index. So this is the we want data first as the first thing, then color. So index 0, this is going to be index 1. Then it's the number of components in this thing. So 3, right? 3 floats for each of them. The data type float, and whether or not something needs to be normalized. Then this is the stride. So now these things are going to be 6 elements apart, right? Because this is 3, 0, 1, 2, 3, 4, 5, 6, right? And that's going to be true for both of them. And the color is going to be offset, I think, 12 bytes from the start, right? Because each float is 4 bytes. So you go 4, 8, 12, boom, start of the color. I'm pretty sure that's how this works. And we can check very easily by just running our command again. So he's actually going to be mad because he's, oh, wait, no, he's good. He's good. Let's see. Look at that. So in our test application, the triangle is off the corner, but we can see that we have like blue down here, red down here, and green down here, right? Like you can imagine as this extends that it's going to get more what we see. So this is what we want to see in our real application. And now if we try to actually run that thing, it's going to immediately fucking crash. So if we run test app on dev DRI card 1, we go, boom, we immediately go, hey, our vertex shader can only take 1 input, which is true. That is what we wrote, because we wrote a lot of hacks when we were doing our initial implementation, because we were just trying to get like the minimal thing that worked. So if we look at Sphero DRM WinSys, we look for pipe shader capability max inputs for the vertex shader. We just up this to 2. We have 2 inputs now. Look at us go. And then we run build.sh and I think we can copy over the new implementation of our OpenGL library. libgallium DRI gets copied to our, like a shared object that matches the name of our driver. And he goes, yo, fragment shader, too many components now. 4 is greater than 0. So we can probably make a guess here that this is going to be the same thing here. We see that we have like vertex shader and fragment shader things. So let's assume that pipe shader cap max inputs here is going to be 4 for the fragment shader. I don't know why 4. Because the fragment shader that we wrote only has a 1 input of vec3. So I don't know where that 4 is coming from. That's a little confusing, but I guess we'll just kind of live with it for now, and maybe it will become apparent as we get farther on. Okay, sick. So now we're going to, we have an assertion here that we have 4 vector elements at line 247. Okay, so what happens here? So as we compile our vertex shader, create VS state, we're compiling a vertex shader, we made the assumption that we only have, for each output, we expect that every output in our shader has GL position of vec4, and that's the only option, right? So now we have to get a little tricky here, where we have to support many different types here, right? But also, we have to mark which one of our outputs are the vertices of our triangle, because the GPU implementation will look for the output that is associated with GL position and use that to render the triangles, right? When we do that triangle render, we basically say, okay, he gave us 3 points, now we have to color them in. And so like the GPU itself needs to know how to do that. So I think that what we have to do is we have to mark which, we have to mark the output that is for that, and then all of the other outputs are kind of like their own thing, I think. I think we'll start there and we'll kind of see what happens. So our GPU implementation, let me think about where this goes. I think we need a new window here, unfortunately. We're going to go to libgpu and we are going to, I guess, add a new API to be like, mark this input, like here is an input, and this is a special input, GL position. Maybe. Maybe. So let's go over to libgpu and we'll look at lib.zig, and maybe it's in the API, GPU shader, right? So here we have push input vec4, push input vec3, and I think we're gonna just change this to push output vertex position. We'll kind of make this its own thing. So we'll say that if it's GL position, we will treat that like a vec4, but we'll have to kind of like handle that specially in the shader. So in shader C bindings now, we need to create an API for that. So what do we call it? We called it vertex position. And we're just gonna give this guy, maybe what we'll do is we will have our shader, we'll have a vertex output position as an index into the outputs. And here we will just say that like this is going to be the output types, items, blend. Okay. Sure, and this goes here. Like that. Then when we run the shader, we're gonna have to do something. So I think that this is done in libgpu. We have execute graphics pipeline, right? And in here, he executes the vertex shader and the fragment shader, and then he rasterizes the triangle with these outputs. So let's see, when we execute our vertex shader, what happens here? We assert that there's only one output value, which is not true anymore. So we're going to have to fix this, but I think we fix this later. We'll fix this later. For now, we just know that we have an API now. If we do zig build, we should have an API now that we can use to just be like, if stir comp, basically whatever's in this assertion here, if we see the thing as a GL position, we treat that thing specially. So it's output vertex position. Okay. Oopsies, I lost the... Fuck. We need this. If this is equal to 0, I guess here we should assert that we have 4 elements, because that is what we are expecting. Then we call libgpu shader output vertex position. Okay, cool. Else, I guess maybe we return here or break or continue. Here we go. Continue. This is in a loop. Then we can handle everything else kind of the same way. So we go switch on var type vector elements. If we see 3, then we are going to do something. If we see 4, we do whatever we were doing before, right? Boom, boom. And then default, we assert false. Maybe we'll do this. Unhandled number of vector elements. There we go. An unhandled number of output vector elements. There we go. Nice. Hi, everybody. Hello. Thanks for the raid, Dishy Codes. Okay, so apologies. I'm not going to give quite a big recap. I kind of just want to stick my head where we will keep my head in the game. So here we're going to be like, if we have 3 elements, then this is an output of vec3, which does not exist yet. So we're going to have to create that function. So in here, we're going to be like, push output vec3, okay? Which means here we have push output vec3, which means that here we just push a vec3. And the reason we're doing it this way is because our C API, we want to keep it like, we have like a Zig implementation of this thing, which has like uses tagged unions for a bunch of stuff, or like enums defined in Zigland. I didn't really want to like redefine these enums externally or define them in Cland and then import them in Zigland. It just kind of felt nicer for like the Zigland to have these type definitions right here. So what we're doing is we're like making C APIs that like convert, that like basically like know which Zig enum or Zig type they want to construct based off of the function. So that's why we're doing it this way. It's a little weird, but it is what it is. And so now this should be fine. Okay. So now if we run this, I think we should get past that assertion at the very least. We're going to hit another assertion, but here we're setting, yes. So we're now at create fragment shader state. I'm looking through the Mesa source code, and it looks like it pretty much does it the same way by marking special known names and handling them separately. Okay, cool. That makes a lot of sense. We were a little curious about the GL position thing before, but it did seem like that's what they wanted. Okay, fragment shader inputs. So here we expected no inputs, and I guess we can just kind of implement the same thing here. So I'm gonna just put a fix me here. Probably duplicated with fragment shader or vertex shader inputs. We do know that like for the vertex shader, we want to handle GL position specially, but probably everything else almost looks exactly the same, would be my guess. So like here we can probably just copy paste this and say we support only a single we support only vec3 inputs here. And let's just kind of see what happens if we do that. Oh, I guess we added colors to our demo app at some point, and at some point we started working on, at some point before now, we started working on shader compilation. Okay, so on draw VBO, we expect one vertex element. So what's going on there? 509. So num vertex elements, what does this represent? I don't know. This is context num vertex elements type vertex element, which tells me the format and stride of this thing. I see. So this is basically telling us like element is equal to like input name in the vertex shader. Like i.e. we have attribute vec3 position and attribute vec3 color. Each of these is an element, right? So that means we have to support elements that are varying. And it looks like we come from our context vertex elements and we look at the source format. So can we maybe go for CTX num vertex elements? Can we just kind of assert this? I'm not sure why we're asserting that we only support vec3 RGB, but I'm sure that there was a reason for it, so we can kind of just keep that for now and then figure this out. So on draw, we say, yo, let's tell him what the elements that we expect are. And here we say create input definitions. So this is basically like the R compiled like representation of these things. What we do is we make like a JSON blob that says where in this vertex buffer are our inputs, right? Because like what happens is like we saw that we have verts, we had like 0.5, like, you know, X, Y, Z, RGB inputs, right? But we had these per vertex, right? So this is kind of was looking more like this, right? And so our definition of this is basically for each thing, like how far apart are they? So for like XYZ, we would say like XYZ has offset 0, stride 6. And RGB, we'd say have offset 3 and stride 6. Except this should be times 4 for everything, right? So that's what this thing is doing. And so we're just saying like, hey, can we push a vector 3 input? And so now I guess we can just go for int I equals 0, I is less than the number of vertex elements, plus I. We're going to say we have another input, and we're just going to propagate the stride and offset. Cool. Which means that that assertion before, this kind of belongs here. That feels a little bit more correct, because this is where we actually care about that, I think. Okay. So now what? We compile our inputs, we pass those things over to the GPU, and then we're fucking chilling. So I think that should just kind of work. Hand wavy. And so let's build and see what happens. Okay, so it looks like we crashed. So it looks like the Mesa stuff worked, but then our actual running, the virtual machine crashed, presumably because we have an assertion in our GPU execution code that is not being correctly handled. So let's take a quick peek there. We'll just, I want to see like, because the output log got kind of like clobbered in some Vim buffer, you know, let's just see. Let's try to run it again. When we segfault there, sometimes if our like virtual machine segfaults or crashes or whatever, sometimes data that we copied over does not get like persisted on disk, so I have to recopy the stuff over to make it happen. That is really not that helpful. Panicked during a panic. Reached unreachable code. So that means that probably in libgpu, we probably have like an unreachable somewhere. It doesn't really, we don't have one explicitly in our source code. So probably what makes sense here is to run our virtual machine with GDB. And when it crashes, he should tell us something interesting. Hopefully. We can hope. Run it. Okay. Root, test, app, dev, DRI, card 1. Do we have to recompile? Yeah, we do. Fuck. Can we go to source, Mesa, build, and then can we just not run this? Just copy the thing over so that it has a second to flush caches if it needs to. And then we kind of wait a second, then run test app, dev, DRI, card 1. Hopefully this time things will work. Okay. So we are in a panic at an assertion at frame 14, frame 15. So we are, right, okay. So this makes sense. Here we're saying this shader has 2 outputs and we only fucking expected 1. So what do you fucking want from us? Because before we were assuming that the only shader output from the vertex shader would be, or that we would either only get 1 output, which is the color, or 1 output, which is the vertex position. And now we're like, what the fuck, there are 2. So we have to track that somehow. Okay. Was it open? It's open here. I see. So our execute for many inputs, I guess, should return. Sorry, let me think for a second. It really depends on what the input to the next fragment shader is. I would love to see the input definition for the fragment shader. Is that something that we can like look at here? Is it like easily accessible somewhere in the call stack here? Up. Maybe. We actually might, hold on, up. Off stride type. Oh, so the input buffer. Right. The only thing where we have like this buffer format thing to look at, where we have like, oh, we have XYZ RGB, that's only for the vertex shader. In terms of like passing parameters from the vertex to the fragment shader, we have to figure that out ourselves, which is kind of interesting. So I would assume, let's make the assumption for now, because we can cheat as much as we want, that the fragment shader can only have 0 or 1 inputs. Then we will create 2 buffers. We can like store them in our like internal representation here. So can we do like shader output? He's gonna have like the special like marked as a bunch of variables, and then unmarked, which is also a bunch of variables. Is that what we want to do? Sorry, let me think for a second. So each shader run will return one of these and one of these. Yeah. Okay. So this is going to return a bunch of shader outputs. And then we can say self shader we need to make sure that when we compile the shader, marked output pause, we'll call it, he needs to kind of propagate this thing. So this thing needs to live here as well. Okay. And then when we compile the shader, we need to specify this. Okay. Which means in the C bindings, that vertex output pause needs to be converted to marked output pause. Okay. And then we will just say, for now, maybe this will give us marked and unmarked as well. This might give us like a shader output. This needs like a single shader output. And here we're gonna say that we have like one marked variable and like one maybe unmarked variable. We might have one, we might not. Those are the two options. And we'll just say, fix me. In the future, we like this only supports a shader with one or two outputs, but that's fine for now. I don't really care. Okay. So outputs. This no longer is like a thing that needs to be freed. And this makes shader outputs doesn't really... This is used here, right? Because this is kind of like storage for the output. So this is going to be unconditionally freed. And then we're going to return, instead of returning outputs, we're going to return... marked is going to be outputs at self shader marked output input, marked output index or something, right? What is it called? We call it marked output pause. And unmarked, like we're gonna say like const unmarked is equal to if outputs len is greater than 1, else it's null, right? But if it's greater than 1, then we do outputs at self shader marked output pause -1 plus 1% the length. I think that gets us what we want, right? Because we're kind of saying that we only support 2 outputs, so this should give us the other one, which is kind of like, you know, a hack for now, but whatever. Sure. That's fine for now. It's not great, but it's good enough. Which means that here we're going to have marked outputs here and unmarked outputs. It's going to be marked outputs is equal to marked unmarked outputs is equal to unmarked. Okay. Okay, I don't know. We're just kind of spitballing. You know, whatever works, works. Then someone is going to call us, and he's going to return shader output. Okay. Then who calls this? Vertex shader execution and fragment shader execution. Okay, so now I guess what's going to happen is this thing needs a dinit, I guess. Because he needs to free this stuff. Right, like this. We need to get rid of these guys, and that means that the callers of this thing are going to call like vert outputs dinit with self alloc and frag outputs. Okay, and then when we rasterize our triangles, instead of taking a bunch of variables, we're going to take in a shader outputs for both of these things. Okay. So now when we do our triangle rasterization, we can basically just look at the relevant pieces now. So like frag outputs, what's going on here? Marked 0 vec4. Okay, and then where is like the vert outputs used? So here we just go right marked here. And I think everything else will probably just kind of work. Shader Zig 230, he's mad because I see. We need to pull this thing out of the JSON structure. Sure. And then here at shader zig 101, we don't need this assertion anymore because it doesn't even make sense. And then unmarked outputs. Sure, we'll put a little nullable on this. That's fine. 102. Why is he mad? Expected type shader variable found optional shader. Oh, because here I need to write question mark here as well. All right. So let's build this and then rebuild QEMU. So hold on. I want to fix this so that I can run the script from any directory. Okay. Let's see what happens now. Presumably, we will get farther. But who knows how much farther? Okay. Let's see. Oh, okay. So failed to execute graphics pipeline missing field, which means that this, we are seeing like the GL clear work, but the triangle is not getting drawn. But we're just getting spam of failed to execute graphics pipeline missing field, which seems fine to me. So let's just work our way through there. Oh, because he's probably not able to we updated the compiler as well, which means that we need to update Mesa as well. Because the compiled thing needs to compile what's got to compile, you know? We changed the inputs to the pipeline, so of course he's not going to work. Okay, so now we're crashing. That's sick. So where are we crashing? We're crashing at execute graphics pipeline, execute on inputs, frame 14, at line 147. So I guess this math is wrong. So we have two outputs, which means that we're crashing on self shader marked output pause +1. Oh, because I didn't fucking... I'm a dumbass. Hold on. Our percent is supposed to be percent len. I'm just a dumbass. Oops. Oopsies, oopsies, oopsies. Alright, let's give it another run and see what happens. So what do we expect to see if this works? I guess we'll expect to see our fragment shader fail to execute properly because he won't have his inputs passed in like he expects. So we need to somehow like take the outputs from the vertex shader and give them to the fragment shader, but we'll get there eventually. Okay. So we are at resolve reference. So this is frame 16. Yeah, so I think that this is saying, hey, we're in the fragment shader, I think. Let's see if we see anything on here that looks like. At frame, I would guess frame 19 or 20. Yeah, we're exiting the fragment shader, and here we have to pass in the correct inputs. Okay. So let's get what we gotta get in there. So here, I'm gonna rename this to execute on buff, because this is taking like input data as a buffer with definitions. But now for our fragment shader, since we're using like our internal representation, we can call this execute on vars. And this is going to be a bunch of variables. I think. And here we're going to assume, we're assuming one input per index. Sure. Which is a little stupid. This is like bad API, assuming one input for the shader. Maybe we can do let me think for a second. We can assume that the inputs are like in order. So we can do like len over num indices is going to tell us like the group size. Yeah. So then we go over group index, and we go, when we execute on the inputs, we're going to go from inputs from group size times num indices. Yeah. Group size times group index is the start. Group end is going to be group start plus group size, which means we go from group start to group end. Solid. Yeah, that works for me. Wait a second, this doesn't make any sense. So this is going to execute the fragment shader. This isn't what we want. This isn't what we want. I'm a dumbass. What we really want is we want the fragment shader to be executed for every single point in the triangle, every pixel in the triangle. And so we're gonna have to do like triangle interpolation. But for now, since we want to avoid doing more work than we have to at this exact point in time, I think we will still continue with running our fragment shader once, assuming the output is constant. But we are going to pass in just the output of the first vertex. We'll just tie it to one of the vertices, and that will give us something interesting to look at. So can we call, like, this is going to be called execute on buff. And then can we do execute on input? Okay, who's going to take in variable inputs and num elements. And this calls execute on inputs. Yeah. And num elements doesn't exist here, actually. I think it's like this. Yeah. Okay. Sure. So here we'll say execute on inputs. And we're just going to take like the output of the vertex shader. If vert outputs unmarked, zero. I guess here we'll say if vert outputs marked len is less than 3. I don't know. Turn. There's no work to do here. We can't really draw any triangles. We don't have anything. Then this is allowed to be accessed fine. This will be, we'll use variable, one variable of v. There we go. Yep. Sorry, I'm trying to think. Var frag input. Yep. We're going to make one frag input, and we're going to stash this as one variable. Okay. Then, if we have a variable to pass in, we will set frag input 0 to that variable. Yep. And then you try to make the inputs. So this is the input buff. And the inputs is going to be a slice of that buffer. So we're going to say frag input buff as a slice. Okay. Like this. Otherwise, if there's nothing for us to pass in, then we should just be able to break block with an empty slice. I think that makes sense. I guess here we can kind of just do this. Okay, which means that here we can pass in the allocator and the inputs. Like this. And I think that that should work okay. Now, what we expect to see here is a red triangle. We want to see a fully red triangle if everything works correctly. Because we're using the first color, which is red. Okay, what's he mad about? Single shader output, I guess, which means that this has to be all the way for now. It's fine. Whatever. And then I guess we can do single shader output for this. For now. And then this doesn't have to get deinit anymore because it's a single output. Okay. That compiled, which is pretty huge for us. Let's see what happens when we run it. Surely nothing good. Nothing good comes from running not well thought through broken code. But maybe. You never know. Give him a second to boot. He's thinking. He's gotta turn on DHCP and shit. All right. Okay. So we're not seeing anything again. But we are seeing. We have a reference to an unassigned variable. Unhandled ref to shader variable unassigned equals void. So what's going on there? What's going on there? Hello, Roboboto. What's up? So we should probably assume that's in the fragment shader. Can we just breakpoint on that? Can we just breakpoint here? Does kind of look like we can. So can we just go again and just see what happens? So we are in. Let's go to like frame 4, frame 3. We're on fragment shader executor. Okay, so we are trying to resolve a reference to a channel in input. So can we print like what am I looking at? Inputs, I guess. So this is a unassigned thing, which makes sense, but how did it get unassigned? So our inputs to this shader run came from the outputs of the vertex shader run. Right? That's kind of what happens. So when we execute our shader, can we look at the vertex shader? I feel like that will give us a clue as to like what we expect to happen. So can we like print inputs fs vs commands pointer, and can we just like, you know, tell me what these things are? These are pretty awful to look at. Can we look at I want to look at like the JSON blob that comes with this thing. So can we breakpoint here just to look at it? Okay, can we look at VS here? How do I like star at 100 at 500? Fine, we'll recompile. It's just easier that way. I guess we could do it on the compilation side, which means that we won't have to restart the virtual machine, which is a big win for us. So I don't want to have to restart it. So can we do like compile? And can we just like std debug print shader is this. Okay, which is going to be what? The output items here? Okay. Noise. So zig build. Del br continue. Can we kill this thing? Oh, it does look like somebody's really unhappy in here. But let's just not think about that right now. Maybe it'll be fine. Okay, there we go. So our GPU shader, our vertex shader, he loads reference. So he takes input 0 and he puts him into number 22. He takes input 0 and he puts him into 23. This seems like a bug. Presumably, we are supposed to be loading 2 references here. Oh, wait. Oh, sorry. This is ID 16. So 14 to 22, which comes from input 0. Yeah, so 14 and 16 both are the same input, which seems like a bug. Then he loads the constant 1 into ID 13. Then output 0 is 19. So then he moves our thing to 38. Our vertex position goes into 38. 38 goes to 19. And then he puts 23 into output 0 as well. Yeah, so it looks like both input and output have like zeros hard-coded, which seems wrong. Right, that's why the output for the color is unassigned, because nobody's ever writing to him. So can we look at like the index lookup code here? So first of all, let's also, if we run this again with ner debug is equal to print vs. Here, before we get to that stuff, we should see what, like, this is what we were converting from. So this is the code that Mesa gives us. Right, so we have 2 outputs and 2 inputs. And here we're supposed to take the variable a pause and put him at 14, and the variable in color and put him at 16. But here we're seeing input 0 for both 14 and 16, which indicates a mistake. So can we look at like in like reference maybe? So here it takes in input index here and output index. So here we're saying like reference source input index 0. So input index here is probably getting the wrong value from Mesa side. So can we look at what command is this? This is load input reference or load output reference, both of these. And we are taking deref var index, which might just be wrong. Ner variable. Index is the identifier for this variable generated by ner index var. So it's unique among other variables in the same index list. So this might be wrong. It would be interesting to see if there is another thing to look at in here. So let's just log, for now, name to index mapping. That should give us a clue. So can we be like deref def or var name goes to this index, right? Let's start here. Here he can't be a string, he needs to be a number. That's a good point. And let's just see what happens if we do that. Okay, so yeah, so this is clearly wrong, right? We're saying a pause 0, encoder 0. So we're looking at the wrong variable. So where does this come from is the real question. So here, 0 and 1, it seems like this is probably where the information is coming from, right? They're saying variable. Oh, this is the attribute here. Yeah, it does seem like this is probably where it's supposed to come from. So can we look at that? This is in decal var. We're looking for wherever they print that stuff. So I think it's in ner print. Can we look for the string decal var? And we're looking for the second thing in some parentheses. Right? So somewhere in here we see this. Components. Location. Components. Driver location, binding, compact. So driver location sounds like what we want. Hand wavy. The actual location of this variable in the IR. Only valid for inputs, outputs, uniforms. Yeah, that looks a lot like what we want, huh? So can we use that? data driver location. And here we're going to use that here and here. All right, let's see if that seems any more sane. Okay, so we have in color 1 and colored 1. That seems maybe good. This doesn't seem good. On the output side, we would have expected the color output to, like, our vertex, our fragment shader should only have one output, right? So in our fragment shader, we have output frag color, input color. Oh, here. So color and frag color are both 0 on this output side. And then maybe that's fine. I think I might have been mixing up the vertex and fragment shader compilation. I'm kind of down to try this and see what happens. So nothing. Red triangle. Okay, wait. That's really good. That's really good. So if we now change our fragment shader to pick instead of the first output, if we choose to pick the second or third, we should see green or blue. So where is this? This is execute, shader, execute, graphics pipeline. Yeah, here we go. So here, let's pick the second input now. Okay, so this should be blue. If this does what we expected, we should see a blue triangle. Like this, I guess. Fingers crossed. Let's see. Moment of truth, baby. Okay, so we run this thing. We look at here, blah, blah, blah. Okay, root, test app, dev, dri, card1. And we're blue triangle. Let's go, baby! Okay, so this is really good. That means that the output of the vertex shader is successfully making it to the input of the fragment shader. Which is very good. That means that we've like parsed our like multiple attributes. Okay, that means that the vertex shader, we didn't actually have to change anything to get it to for the shader to like behave the way we want. And it looks like for also the fragment shader, we didn't actually have to implement any new instructions in the GPU shader to output the input attribute, which makes sense, right? The actual work now is going to be trying to do interpolation on this triangle before we call the fragment shader. So, when we rasterize triangles, what's going to happen here? I guess we have a color associated with every single vertex. Maybe. It's like a maybe associated variable, right? And I guess what we're going to have to do is we're going to have to like interpolate those 3 values for each triangle, right? So we have like vertex outputs. We have marked len over 3 is a triangle index. And for here, we're going to say like const colors, frag inputs, I guess we'll call it. There's going to be 3 variables. That are going to come from the unmarked section here. It'll be easier for us, I think, if we just assume these are vec3s. Yeah, let's do that for now. And we'll just say, fix me assumed vec3 valid input. This is like totally wrong, right? We need to fix this. So we need to fix me what if the shader has no inputs, and fix me what if the input is not a vec3. But we can tackle that in the future. That's a future me problem. So, what are we going to have to do? We're going to have to, as we walk, each pixel coordinate of this triangle, we have to know where on the triangle it is. So we need like barycentric coordinates. So if you just like, if you are in a triangle and you want to know how much of each of the three corners, how much of each of these corners you want to use, you need some sort of thing that says, okay, we know that like for this triangle, if we are here, we're at 1.0, and if we're anywhere on this line, it's 0. Right? As we get farther away from this thing, it gets closer to 0. If you assume like linear interpolation, you could maybe try something like where you raycast out to this line and you figure out like where, if you like raycast through the point to the line, say you've got like a point here, you could do something where you like raycast through this point and figure out like this is like 1.0, this is 0.0, how far am I, right? You could do something like that. You would need to know you would need to figure out like where on this back edge you are, but I think that would be doable. That's like what I thought of when I was thinking about this. But it turns out if you just look up triangle interpolation, somewhere you find, I think here, this, you might end up with the idea of barycentric coordinates. Yeah. You come across this idea. And what this thing basically says is instead of trying to like figure out where along this line you are, you can actually do something that's similar conceptually, but easier, like very easy to calculate, which is what is the area of this triangle over the area of the full triangle. And it turns out this is quite easy to calculate. I was reading barycentric coordinate on Wikipedia. And in the Wikipedia article, they have a chapter here that talks about specifically its usage on triangles. And the short version of this is the area of a triangle is quite easy to calculate if you think of it as half a parallelogram. So if you like take like, you know, when you're working with like 3D vectors, you kind of have like your two fundamental building blocks, your dot product and your cross product. It turns out that the cross product here is super fucking sick because the cross product is easy to calculate. You just take like, you like the, if you draw like your numbers as like x1, y1, z1, and x2, y2, z2. If you draw like kind of like diagonal lines through this thing, I think you'd have to do like you have to add in I, j, k here, I think. You draw like diagonal lines to this. So you go like x1, y2 plus is like your new z. Your y1, z2 is your new I, and then your z1, x2 is your new j, but then you have to subtract the other way. So you go like diagonal down to the right is all added, and then you subtract backwards. So you go like x1 minus x1, z2 on the j, minus x2, y1 on k, minus y2, z1 on I. Is kind of like how you calculate this new vector, and this new vector is like an arrow that points perpendicular to your other two arrows, but the magnitude of that thing represents the area of a parallelogram, and a parallelogram is just two triangles, right? You can just, if you were to take your vector AB, and you draw like this parallelogram, right? You'll notice that the triangle of AB, and you call this C, right? If you have A, B, C, your triangle area is just half the parallelogram area. So, all of this to say, in order for us to figure out where we are in a triangle, we can calculate the cross product of the overall triangle as well as the cross product of one part of the triangle. So if you're trying to figure out how much of this component of like A is represented by this point, you take the area of, we'll call this like P and B and C. All you have to do is take the magnitude of BPXBC over BAXBC. Because these gives you like parallelogram areas, but the 2 times is like on both sides. So it should be fine, I think. Because this will give you like equals 2A equals 2B, the 2's cancel out. Yeah, something like that. Something like that. Yeah, so let's start trying to figure out how to do that. I want to make sure that I'm right about the cross product here. I'm pretty sure I am. And since the cross product is a vector, we're going to need to like extract the magnitude from that thing, which I think is just a squared plus b squared plus c squared square rooted, Pythagoras. So can we do like, we'll cross a vec3 and b vec3 and return a new vec3. So this should give us, I think it's, what would we say? It's like, you draw the diagonal lines. So your var ret is a vec3 is equal to undefined. You have ret 0. If we look at this really shitty picture, the I component comes from y1 z2 minus draw our arrows. This is, okay, y, z, I. So we're looking for the thing that wraps around, I think it's y, z, I here. Yeah. So y1, z2 minus y2, z1. A1 times B2 minus y2 times A2. This is going to be fucking hard for me to get right. I think that this is right. And then we just know that we go down 1 for each one. So 1, 2, each of these numbers is increments. But wrapping around. I'm just kind of like pulling this out my ass. But let's just see if this is right. And if it's right, then we can move on. But if not, then we can look a little harder. So let's maybe, what's the easiest way to do this? I think that we can confirm easily if we just pull up like Python and Python 3 packages numpy. And can we do like a, maybe we'll pull this into like a test.zig. Const vec3 is equal to a 3 f32s. And we'll import the standard library, and we'll do pub function main. And can we just do like cross std debug print? Let's do any, and we'll print out. We'll make some a is a vec3 is equal to 1, 2, 3, right? We won't think too hard about it. B is going to be 4, 5, 6. And then we'll do print out cross A, B. Zig run source test.zig. So we get -3, 6, -3. Can we do something a little less symmetrical? 4, 9, 6 or something? Okay, there we go. -1.5, -15, 6, 1. So if we go into Python 3 and we do like import numpy as numpy, and we do like numpy, can we do like numpy cross product? I know it exists, I just can't remember. So this will take in A and B. Okay, so A is going to be like, what do we say? 1, 2, 3, and B is going to be 4, 9, 6. -15, 6, 1. -15, 6, 1. Okay, we're fucking chilling. We're chilling. We have successfully implemented the cross product. Sick. Let's just copy paste this back to make sure that we have the right one. Just in case we made a mistake. I'm shocked, honestly, that I got that right. Because this is like not really legible in any way, shape, or form. Like, what are we looking at? But we got there. We got there. Diagonal forwards minus diagonal backwards. It's simple. Okay. So let's look at shade. This is in lib.zig. I think this is what we had written, but let's just make, just for confidence. And then can we do like magnitude? What is like the word people use for this in like game programming? When you do like, you take vec3 and you do length, I think is usually length. That's the word I usually use for this. So here we're gonna do just v0 times v0 plus v1 times v1 plus v2 times v2, and then we square root this thing. A squared plus b squared equals c squared. Yeah, I'm pretty sure this is a good length. Pretty sure. PQ system, thanks for the tier 1. I can't remember if I thanked you for that, but if I didn't, thank you very much. Much appreciated. So this should give us everything we need. So can we, maybe we go to test.zig and we just say const lib is equal to import lib, then we don't have to worry about copy pasting functions back and forth. Can we do something where, how do you calculate the area of triangle like the normal way? It's like 1/2 base times height, right? Yeah, 1/2 base times height. So if we define, can we maybe define a triangle? Maybe we define a plane in Blender. We bridge these two things. We delete this vertice, and we make a face here. Can we like? I just want to like position this thing in 3D space somehow. Right. I just want to like do something like off axis. And then can we like calculate, if I like select this edge, can I like get the length of that thing? Not trivially. But that's okay. That's okay, we can figure this out. So so if we're doing 1/2 base times height, we know that each of these edges is 2 long, which means that this is, if we scale this down by 0.5, this should give us something that is, this will give us a 1, 1, root 2 triangle. 1, 1, root 2. Which means we still have to calculate this. Oh, but we know that this is the area of this is, hold on, I'm a dumbass. Make this bigger. So the area of this is 2 times 2, 4. The area of this is 4. Which means that if we delete this, the area of this should be 2. Right? This triangle should have an area of 2. And then we can just kind of like rotate this around. And take the values of these vertices and try to calculate the area. And we should see something that gives us 4 if we can take the magnitude of the cross product. That's what we should see. Or an area of 2 for the triangle. Except we need all 3 points, not just 2 of them. So we need to calculate the differences between them. Okay, so we have A, B, okay, and C, which is this one. Okay, so we have A, B, C, right? If we do, we need to take 2 of these. We don't really care which 2. So we'll do const. We don't have like a vector sub right now, so we'll just do this here, whatever. I guess these should go on like members of a vec3 structure later, but we'll come back to that, I guess. So let's just do for now. You know, we'll figure this out later. Return var ret is a vec3. Return, there we go. A0 minus B0. 1, 2, 1, 2, okay. So we do const AB is equal to sub BA. We have AC is C minus A. And so the area of this thing should be cross AC, AB, and AC. This should give us a thing with a magnitude of 2. So here we'll say const cross is this. XAB AC, I guess we'll call it. And we'll call the area should be the magnitude of that. Yeah, so we'll say we have XABAC with this area. What's he pissed off about? Sure. This squirt needs to return. I'm gonna call my first norm except good. Nice. This VGPU is an educational project, right? Yeah, you could say that. You could say that. It's educational. I mean, we're doing it to learn. I don't know if I would consider this educational content, but yeah, sure. I'm trying to learn. So this is a really good sign. This is a really good sign that our cross product has a size of 4 with this like arbitrary vector, which means that this makes sense, right? Because the plane we made was a size of 4, and then we cut it in half for this 2, which means that the parallelogram is right. That's pretty sick. That's pretty sick. I think we have like somewhat reasonable confidence that we can calculate the area of a parallelogram. So now what we want to do is figure out how to work with that thing, right? So as we walk the pixels of this thing on the screen, we need to know like how that thing is tied to the object in 3D space. Oh, which is not super trivial, huh? I wonder if like, do you think that it's the same in 3D and 2D space? Like if I have like this triangle and I'm looking at like this, and I want it to be fully blue here, fully green here, fully red here, do you think that like if I worked in the 2D projection of this thing, like here, that I can just work with this triangle instead? You think? That'd be kind of sick. I don't really see why that shouldn't work. Right, like the gradient would move much faster, right? Like if this is supposed to be blue and this is supposed to be red, and I like, this is gonna like be a very quick transition of blue to red here. But that's like kind of correct. Versus like this. If you do it naively, you have perspective incorrect interpolation. Okay, so that it is not the same. Old games had warping due to this. Oh, hell yeah. I like that the people in my chat just know the answers to these like stupid fucking questions I'm asking. That's so fucking sick. I guess we did fix shader compilation, and at some point we started implementing this. I've been really bad with the timestamps. Okay. Search perspective correct barycentric coordinates. I assume that I just have to work in 3D space, right? I don't want to read this right now. So we have a couple options. We could do the stupid thing, right, for sure. Or we could try to figure out the right answer. I'm okay with just doing the stupid thing for now. And then maybe leaving the 3D manipulation part as an exercise to the writer. Right, because like, it'll give me something close. Yeah, okay. Let's do that because I don't really I didn't really consider the fact that I'd have to think about this until right now. So the reason that I'm thinking about this is because right now we're rendering in 2D space. We take the triangle and we just say like what are its x and y coordinates? We just discard the z coordinate and we convert those into pixel space. Then we walk pixel by pixel. So if we were to do everything in pixel space, it's just easier. It's just easier, even if it's wrong. So let's think about that for a second. So we have like a triangle that we're trying to render in pixel space. And we know what the coordinate of that pixel that we're writing is in pixel space at any given time, right? Here we know, because like just the way that we're walking this thing, we basically walk by like y pixel and x pixel. So we have an exact x and y pixel in like the texture output. Which means that our cross product now you can kind of just ditch the z coordinate of this, right? Because if you're working in 2D space, oh, you only want the z coordinate, sorry. You only want the z coordinate, right? Because if the cross product is like a perpendicular arrow to your two vectors, right? Perpendicular to each of these, and with its magnitude of the area, if our two arrows have no z component, then we know that the other thing has to be perfectly aligned in Z because Z didn't exist in the input. So maybe we'll do like triangle area, parallelogram, pgram area, I guess we'll call it for now. We're going to take in AB, which is going to be represented as a pixel chord, which is kind of wrong, but that's fine. Maybe we'll just call this, yeah, it's fine. And this is going to return a F32, I guess. So this is just basically going to be this. Okay. Sure. Now, when we're rasterizing our triangle, I would like to, instead of trying to hook up to the fragment shader, start by just trying to assume that every vertex, I just want to like just color each of the vertices, hard code them as red, green, and blue, just to give us something to look at. I think that'll make sense. So how do we do that? When we're rasterizing the triangle, we set the color to the frag color. So here, I guess we are going to, we take in three vertices, A, B, and C. And we sort these according to the height, which makes them easier to draw. Because then we can do like 2 halves of this triangle. We can just kind of like go row by row this way. So we know that in our world, this is always A, B, and C. Now, if we want this to be red, so when we're drawing the CBA triangle, sorry, when we're drawing the first half, we draw it bottom up, which is maybe stupid. But we're kind of drawing this triangle first. We know we probably need the area of the whole triangle initially, right? We almost certainly need that. So let's do P area of, these are in pixel chords. So we need sub pixel chord as well. Which, you know, again, we'll clean this up later, but we just want to get something. And I think these pixel chords are U32. I'm just going to make these I32s for now, because I think that'll just make everything easier to work with. Oh, but you can't iterate I32s. Fuck. Okay, I've changed my mind. I want to work in world coordinates now, which will make things maybe easier. So how do we do that? When we sort the triangles, when we sort the vertices here, we need to keep track of the indexes that come out of this thing, or the colors that come out of this thing. Or we at the very least, we need to keep track of their initial positions. Yes. Okay, so here we like convert all of these guys to pixel coordinates. And maybe we should output to this. We will do homogeneous to pixel chords. This will return some pixel chords. Great, right? Then we're gonna do like sort Sort chords by pixel Y. Uh-huh. And he's going to take in the pixel chords. And now what I want to make sure that I'm doing here is that I want to return I don't want to return the sorted pixels. I want to return the index order, which must exist. I assume that that exists somewhere in the Zig standard library, right? I want like I want to give like the indexes instead of giving me like 1, 2, 3. I want to okay, if I have A B C like this, instead of it and I give it the vector B C A, I don't want it to return me A B C, right? I want it to return me 2, 0, 1. The index is in this because that way we can keep the original vertex positions tied to these, which will be important, I think. As long as they have something like that. Like, I know there's a word for this, but I just don't know what it is. Argmin? Arg something I've seen before. Like, is there like a name for index order to sort buffer? I've definitely seen this word come up before in like PyTorch. I think it's just that sort might just like return you. I've definitely seen it here, indices. Yeah, okay. So maybe Zig just doesn't have this. Let's see. In Zig, can I get the sorted indices of an array? Question mark. Fuck. Okay. Jesus. Oh, I guess you can sort. Right. What he's doing is he's creating an index buffer and then sorting that according to the external data, which makes sense. We can do that. That's definitely doable. So here can we return like we can do like ret is going to be 3 u8s is equal to 0, 1, 2, right? Simple. Then we take in the index here and we take in the context, which is going to be the pixel chord. Yes, 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 yes. So then we can do context LHS, or I guess we were doing it other way. We did RHS first. LHS like this. And then here we need to pass in our context, which is going to be pixel chords. Like this. Yes, and we would sort the red, and then we return red. Oh, baby, that feels fucking good. That feels good. Which explains why this context thing exists at all. So we can do homogeneous to pixel chords. And then sort chords by pixel Y, and we take in the pixel chords. Which I guess we can just kind of take these in like this. And then const sorted indices equal to this. Okay? Then let's just see that everything works the same. If we do pixel chords sorted indices 0, 1, and 2. Let's just start here. And then maybe we print these out. So std debug print pixel chords. And we'll say, yo, this is the pixel coordinates. And we'll say the sorted order is going to be sorted indices. Sure. Let's just start there and just see what happens. He's mad because here we probably gave the wrong context somewhere. And one of these things is supposed to be the context. Sort, we give the items and then the context. This. Oh, and then here, this probably needs to write const. And this takes in... I'm confused. Expected type const pointer to 3 232s. Found slice to... Ah, fuck. Okay. So do we do... If I do, like... chord slice is a const pixel chord is equal to pixel chords. Does that work then? Is it just like some like type coercion shit? Yeah, it is. I see. Okay. So can we just do like a ninja and run this thing? And let's just like see what we get out. Bump. Fuck you, ChatGPT. Oh, you did help me that time. That was a good idea. Root test app dev dir card1. Okay. So here we're seeing 576, 576, 192. We're seeing sorted 0, 1, 2. That doesn't look right. Oh, we want to go big to small though. Yeah, we did do right hand greater than smaller than left hand. I guess it doesn't really matter. So if we flip this, we should see the 192 come first, then the 576 after. And then we don't have like tie break on the X, so it doesn't really matter. Doesn't really matter, but it should be fine. All right, root test app dev dir card1. What? Oh, it does matter. The indexes they have to go in the other order. Oops, they do have to go in the other order. But did I not get like a little print before that? Oh, I did. Okay, sick. So now we see that the indexes are coming in the right order, but now it's crashing because we do need to do the smaller ones first. Okay, sure. So this should just be called greater y. That's a better name. Which is kind of backwards. That's stupid, but it is what it is. We were rasterizing our triangles the wrong way around for some fucking reason. Okay. But now that we have this, we can pass in the colors in the same order now. Or like, yeah, we'll do colors for now. So for now, we'll just do 3 U32s. Okay. And I guess we want its like, we want like the original positions as well. So we'll call this like original chords. Okay? So then we have to pass in what? As we walk this triangle, we're going to be like here in pixel space. We need like a reverse transform to know where we are on 3D space. So I'm back to not liking that. Because that sounds hard. So instead, what can we do? How can we represent this? So we have the vec3 here. We have the pixel chord, and we have the color. We have all three of these things. Now, what we only have here is we only have the pixel chord. Yeah, I don't want to figure out like the reverse transform here. So I'm back to wanting to do this in just flat 2D. And the reason we stopped doing it in like 2D space was because everything was in U32s, which is just kind of like hard to work with mathematically. But we can just upcast those to like 32s for now and then call it a day. Sure. So we'll take in the colors. And now how do we determine as we're walking this thing where we are? I guess we're probably going to take in the triangle and the colors. That's kind of just how it seems like it's going to work in my mind. And we are going to have to determine, we're going to have like the area, total area is going to be p gram area of sorted triangle 1 sub PC of 1 to 0 and 2 to 0. I don't know. Whatever. Then, as we are walking this thing, we need to find the area. We have like our point, and we need to calculate all three areas, I guess, right? So we're going to be like, so if we're looking at this point, we'll call this 0. We want point to point to 1 and point to 2, right? 1, 2. So we have our y pix. We're going to look at this. We're going to do this pub const signed pixel chord. Okay. Then when we do sub, we're going to return a signed pixel chord. So we'll do like as I32 int cast. Gross. I know. It's just easier this way. I know. Okay, but good enough, right? Now when we do p-gram area, we can work with S pixel chords like this. And now all of this should work a little easier. So we'll call this P PA is going to be the point. So we have the const P is going to be an S pixel chord. And we're going to have our XPX and our YPX int cast from U32s to I32s. Okay. Okay, that looks good. PA is going to be sub sorted triangle 0 to P. PB 1, PC 2. Okay, wonderful. Now we can say p-gram area of PB PC over total area is going to be the color A amount. B is going to take out the A, and C does not use PC. Okay. Okay. So this is like the ratio of the colors. I probably got some of these like orders wrong, I would assume. So let's just start by doing std debug print colors. Okay, let's just kind of see where that goes. Color A amount, color B amount, and color C amount. Okay, now we just have to kind of fix this. So we go, discard the colors. And when we call rasterized triangle, we'll just call it with, something that's like RGB or something, right? Let's start there. Zig build. Does it compile? He does not compile because he found two I32s on sub PC. Yes, this should be a pixel chord like this. He doesn't need to be signed. It will automatically sign himself later. Okay, and then XPX expected U32 found U size. So int cast this. I guess he does actually. I lied. The int cast is necessary. It's just from U size to U32 instead of U32 to I32. This compiles. Okay, so let's just like fucking run this thing and see what happens. Ninja. This much coding requires exercise or theory? I don't really understand that question. Although, if I had to guess, I would guess, I don't really know. I find it hard to distinguish theory from practice. I think generally my way of working is that I pick up theory by practicing. So it's not like I'm like studying coding or anything. I'm just kind of like trying stuff until I get an answer. Okay, this is fucked up. But I mean, these three things do add up to 1. We're not new lining, which is annoying, but we do have things that add up to 1. And they do seem to be varying as we iterate. So like as we go left to right, we do see like 166, 166, we do see like changes, right? We see like less of the first thing and more of the second thing. The signs are wrong. I'm going to ignore that for, I guess it's the sign of the second thing is wrong. So here we'll just swap C and A here, and that should kind of like fix itself. Because there's some sort of like clockwise counterclockwise thing going on. And now if we got this right, we should be able to like interpolate these colors, which I don't really know how to do. The colors are this like, they're kind of like as U32s right now. So we have like a U32, which is like alpha, blue, green, red, or something like this, right? And we kind of want to interpolate this thing somehow. I guess if we have everything is less than 1. What I'm worried about here is if you like add these things together. Is there like overflow that we need to worry about? If I have like, let's think about instead of like base 2, we think about like base 10, right? Say we're storing like something in each digit of a base 10 number, right? So we're saying like 9, 5, 4. If we divide by 2 here, the components leak out, right? Because like 5 divided by 2 is 2.5, which would mean that we would get like the half of this thing over here. So I think my gut says that we need to like extract the red, green, and blue components and then interpolate them individually. Hand wavy, that's just kind of my guess. So, which makes me think that we should do some sort of like shifted interp. Which gives us like 3 colors. As well as like proportions. And it's going to return us a U32. And we want to take in like a shift as well. Which is U5 or something. I don't know. So we're going to do like, if our shift is 8, we're going to go like A shifted right by 8. And we're unconditionally masking out the bottom 8 bits. Yeah, okay. So we do like shifted A is equal to A shifted right by shift is a U8. And 0xFF. I don't know, man. I feel like we've like overcomplicated stuff somewhere, but we're kind of, we are where we are, so. It is what it is. Now we do like SA times proportion of A plus SB times proportion of B plus SC times proportion of C. This is going to be mad because these things often be int cat. So we're going to do like, these are F32s, and we'll do like float from int on all these. Ugh. Ugh. I hate it all. I hate it all. But we've made our bed, and now we have to sleep in it. Okay, so now we have like interpolated is this. And we want to turn this back into a U32. So float from int from float. Hey, how's it going today? Good, how are you? I am stoked. We have triangle interpolation on the way. So this interpolated value, we just have to make sure that we mask this thing back off and shift it back up. So like this. And we're just gonna be like, fix me, what the fuck are we doing? Bitwise manipulation. Why are we storing colors in a U32? This is stupid. But now it makes it so that we can get like the total color here. We can just do shifted color interp 0 with colors 0, colors 1, colors 2, as well as color A amount, color B amount, and color C amount. And we just say that the output color is equal to this 3 times, 4 times. Bitwise ORed together. What the fuck are we doing? So we'll just kind of like do each of the colors individually and then bring them back together into one final output color. I think there's a chance that that does what I want. Like a non-zero chance. Maybe I'm at like pretty high confidence actually. Maybe 85% confident that'll do what I want. That's pretty high. We're often at like 30%. And you know you're writing good code when you're like, I'm 30% sure that the code I wrote does what I want. It's like, maybe you should get a little better, more confident. But you know, we gain confidence by running it, so and testing. So it is what it is. All right. Oopsies. Test app. Okay, let's moment of truth. Oh, let's fucking go, baby! Look at that shit. It's slow as all hell, but that's a fucking interpolated triangle, baby. Let's fucking go, dude. So we've hard coded the colors for sure, and our thing is fucking crashing. So let's just maybe fix the color values to be not hard coded. So how do we do that? We want to turn our colors into like, we take the output of the fragment shader. You know what? Oh, do I want to keep going? Do I want to keep going? It's worth doing, right? But my brain hurts. Okay. I think that's a big fucking win. So there's one missing piece of this that we haven't done yet. So we kind of like, we fixed our vertex and we fixed our fragment shader so that it could run on an individual coordinate, right? And we updated our vertex shader so that we could export a color from the vertex shader to the fragment shader. And then we also implemented triangle interpolation, which means that we can assign colors to each of the 3 vertices and interpolate between them. Now, what we have not done is we have not run the fragment shader with the interpolated output of the vertex shader. But I think that we have accomplished a lot today. It's 4 o'clock. My head fucking hurts. So I think that that is a good place to call it for the day. The next steps are going to be that we have to run the fragment shader on every pixel. And it can't be on interpolated colors. It has to be interpolated fragment shader inputs. But I think we will leave that for another time. I have not decided at this point if I'm going to do that in happy hour or not. I have to decide what I want my next mainstream to be. So I'll think about it. We'll come back tomorrow. We'll do something fun. Thanks for watching, guys. If you like what you saw, we stream most days at around 12:30 Pacific time to 4 o'clock Pacific time. It is 4 o'clock Pacific time now. So if you are watching live anywhere between 3.5 hours ago and now, if you're watching on Twitch, there's a YouTube link in the Twitch description. If you click on that link, you will see our channel where we have all of our previous VODs organized into playlists. So if you want to check out the background on the GPU project, or if you want to see some of our other projects, those are all available. Google Maps replacement, QR code decoder, operating system, like video editor. There's some interesting stuff in there if you want to check it out. If you're watching on YouTube, there's a Twitch link in the YouTube description. You can swing by and say hi if you feel like it. If you guys want to see the 12:30 to 2 segment, not the 2 to 4 segment, those are behind YouTube member stream or YouTube member or on Patreon. However, if you catch them live, there is no paywall. So if you want to watch 12:30 to 2, where do we do happy hour, which is just kind of like more laid back, less rapid progress, less intentional feature, kind of more just clean up. Like if you were like, if we were to commit this code that we committed today, future us would hate us, right? So happy hour is kind of like the idea of I have work that I want to do to clean this stuff up, but I don't necessarily think it deserves a YouTube video. But if you want to see it, there is paywalled content for that, or you can catch it live. What else? Is that all the plugging we have to do? I think that's it. YouTube, goodbye, and Twitch, let's find someone to raid.